Okay, this is the second part of a lecture on elastic collisions in two dimensions. We've already done most of everything that we're going to talk about here. Everything I'm going to talk about here you've done in previous classes. It's just that we're going to combine all of this together for two-dimensional elastic collisions. And this is actually going to encapsulate almost everything that we've done in collisions in this course. And we've done a lot with collisions, in both one dimension and in two dimensions. The previous lecture was talking about the geometry of the situation, right? The geometry of two balls colliding. And that's very important. You have two balls colliding. That geometry is absolutely necessary to look at it. If you've ever tried to resolve a collision between two billiard balls or something like that, when you were looking at a Physics 1 textbook, you look at that, you see the conservation of momentum, you see the conservation of energy, and you say, okay, this is really great. I've got a really powerful tool here, and these are really powerful tools. And then you say, okay, now I want to do this with my billiard balls, and I want to see what angle the ball will go off at if I strike this ball with that ball. And you figure out that you don't have enough information. You end up with a parameter somewhere in there that doesn't disappear. You have, I think it is two equations or three equations, I'll say, three equations and four unknowns. You need one more equation to fix that up. And that equation is going to come from geometry. And we've already taken care of that in the previous lecture. So the previous lecture was all the geometry. I'll show you those in a minute, and I'll run through that really quickly. But the lecture today, or the second half of this lecture, is all about the physics. How do we actually change the velocities in this collision? Okay. This is where we ended the last half of the lecture, and we'd just gone through all this, and we'd been looking at what happens as the ball goes down this line. This is the line that the ball would have gone down unimpeded if it didn't actually hit this green ball. So the blue ball was going down this blue path, but it hit the green ball, and now that path has got to change, right? And the things we had to worry about there were, one, what do we know about the balls? That's not anything in geometry. That's just some programming stuff. We have to keep track of different things. The mass and the radius of each ball, those don't change. The position and velocity, both of those change. The position changes in the update function. The velocity, that changes during the collision resolution. So the velocity is what we're going to work on here. Everything that's going into the position, that's going to be the geometrical things in steps 1 and 2. The first one of those is collision detection, right? Do these two things actually hit? And we figure that out by whether or not they overlap. If the two shapes overlap, then they hit, because two things can't be in the same place at the same time, right? People have been telling you that for a long time. Your dad probably told you that when you ran into a wall. So we just have a way of doing that. With two balls, it's really easy, right? With two squares that don't rotate, it's really easy. Now you have squares that start rotating, it gets a little more difficult. We've already done it for just a wall and a ball, and that was difficult enough, right? And now imagine if it had more edges. So basically that was just if the distance between the two balls is less than the sum of the radii, right, less than the sum of the sizes of the two balls, then the two balls will interpenetrate. As soon as that happens, we want to resolve a collision, step back, go back to the previous position, and then resolve the collision and keep the balls from ever interpenetrating. So that's the whole point of this collision resolution algorithm, is to keep the balls from interpenetrating, have them bounce around like real balls, and everything's going to be hunky-dory. Then we found these collision directions. So we have two directions. One I call the normal, because it's the normal direction of the of one of these circles, right, of one of these balls, and that is just the direction between the two centers of the two balls. All right. That's what we're going to use as our normal direction. And that is just ratio of the displacement, which is a vector, to the distance, which is the magnitude of the displacement between these two balls, right? The position of the second ball minus the position of the first ball is the displacement, and then if you find the magnitude of that, that's the distance between them. So now we have a unit vector because we've divided a vector by its magnitude in the direction of we're interested in. And then we found the tangential direction, which is just a combination of those same two components, a different combination of those two components. There's some more general mathematics involved with that. We're not actually getting into that in this class. You'll use it a lot when you get into advanced mechanics. So we've got this initial condition. We want to go to this final condition here where the balls are going off in different directions, all right? And to do that, we're going to need physics. We're also going to need these normal and tangential directions, so I'm going to keep them around for the next couple of steps until I don't have enough room for them anymore, and then I'll get rid of them. So we're going to use these two directions to help us figure out what to do. Again, remember, we want to go along this line, right? And so if we're going to go along that line, we only care about the impulse along that line because that's where all the impulse is, because this is an elastic collision, right? So all the impulses along the line between the two centers, so everything's only going to change there. Only that component of the velocity will change, all right? So normally we've been talking about components of velocities prior to the slanted tunnel, prior to Galton's board. The components have always been the x and the y component. But because these are vectors, the whole point of using a vector is that it doesn't really matter what coordinate system we use. It doesn't matter how we rotate our coordinate system. If we sum the components, we still get the same magnitude. Or if we sum the squares of the components and take the square root, we always end up with the same magnitude. It's always the same vector, right? It doesn't matter what we do with the coordinate system. The vector is independent of the coordinate system. We measure it in different coordinate systems. Now we want to use the most convenient coordinate system for this particular setup. And we talked about that in the slanted tunnel and Galton's board. And the whole reason for that is that we want to just do one set of mathematics for one set of components, one for each ball. And that's going to be in that normal direction. That tangential direction, nothing happens. So we still have to break everything up to figure out what the component is in that direction, but then we just save that for later when we recombine the effects of the physics. So we do the physics, then we recombine things, and we're okay. So breaking these things up into these two components is just a matter of your normal sort of projections. So a projection is just the dot product of a vector with a unit vector in the direction you want to find its components in, right? So that's v1 dot the normal direction. So the velocity of the original ball dot the normal component there, and the dot product again was just the sum of the components, this pairwise sum of the components of the two vectors. So that's v1 in the x direction, the x component of v1 times the normal component, or the x component of the normal vector, plus the y component of v1 times the y component of the normal vector, and that's going to give you this projection. You'll notice the projection is smaller, it forms a little right triangle. And all those things, they're part of what part of the meaning of all this. Okay, so where are we going to go from here? Well, we also have to find that tangential component. It's exactly the same thing, right? And we've done this a couple of times in the past. We've done this in the last two projects, so this one's going to really drive it home, and now you'll never forget it, right? You'll know this for the rest of your life. It's going to be one of the most amazing things that you'll tell your friends at cocktail parties. So you do the same thing. You just find the projection of v1 in the tangential direction. And you would, if v2 were moving, you would do the same thing for V2, for the second ball. If the second ball were moving and V2 was not 0, you do the same thing for that second ball. I won't do it here. I'll list it at the end when I have my list of all of the all of everything. When I do the overview, I'll have that there for you, but it's the same equation. So now that we have that information, what we want to do is we want to flip V1, right? We want to change the direction of the velocities. Actually, we want to do this for both velocities. And this is the same sort of collision resolution that we used for the colliding wheels in 1D bowling now, because we're only dealing with the normal component, right? Since we're not using the tangential component, only using the normal component, we're now in a one-dimensional situation. We're in one dimension. We're going to do great. That's all we need to do, right? So what do we do to do that? We need to do the same thing we did, and that was a lot of work with kinetic energy and momentum and so forth and so on. And we ended up in 1D bowling with the fun little equation like this, where you have a the new velocity in the normal direction being a sum of different components from the two of the normal velocities in the other two of the two different balls. And the same thing for the second ball. You need to do both, even if one of them was originally 0. And so everything is in that, right? For the upcoming situation, right, the two masses are going to be equal. And you notice there's something really nice there if the masses are equal, right? And that is that the new velocity is not going to be of an object, will not be dependent at all on the old velocity of that same object, right? Because you have a m1 minus m2, m2 minus m1. Those two quantities are 0. So instead, you have, for V1, you have V prime of n is going of 1, V prime of 1 is going to be 2m2v2 n divided by m1 plus m2, but m1 and m2 are 0, so that denominator is 2m, the numerator is 2m, so that just means that you have, a swap of the velocities. So if the masses are equal, you have a swap of the velocities, just like in high school physics, right? Nothing new, nothing amazing. Very simple to program. And that's all you'll have to do for this exercise that's coming up in class about the simple pool shot. And you can look at that again on that URL down there. But, for your final project, for a mini project, possibly, depending on what we're using for the mini project this year, you might have to use something more complicated. There it is. It's the whole shebang. You can use that when you want to, and that's what you do. I should note that I've drawn this longer line here for the V prime. V prime 1n is fairly long over here. It should be short. It should be actually 0 for this particular collision, but I wanted to have something exaggerated so that you could actually see what was going on, what I was doing while I was talking about it. All right. Now we need to recombine everything. We've resolved the collision. We've done the physics part. Now we have to do a little bit of vector algebra, put everything back. This isn't going to be really difficult. It's just vector addition, so head to tail sort of stuff. So we're going to add v1 prime n in the n direction to v1t in the t direction, and that'll give us what we want to do. We did this in the slanted tunnel. We did this in Galton's board last time. Very, very simple. So we've got all the information already that we need for that. We've done the calculation for v1n. We multiply that by the normal vector, right? That normal vector is unitary, so the unit normal times v1n is a vector in the normal direction with a magnitude of v1n, right? And the same thing for the tangential direction, and all that together, you've got the collision, all right? And finally, you have the opposite direction. I guess I'll have to put one more video together that'll just be an overview, but this is all you need to know.